Hello everyone, today I'm going to give a talk about my country research. The topic of my research is an analytical model for budget allocation in risk prevention and risk protection. This presentation will consist of these 6 parts. The first part will give the background and the introduction of this research, and the second part will present how the problem is modeled and formulated. Then the model result will be given in the third part. To validate the model results, the risk examples and the experiments are given and conducted in the fourth and fifth part. Then the conclusions are summarized in the final part. The future research directions will be discussed. Now let's start with the introduction. In project management, the project risk is defined as an uncertain event or condition that, if it occurs, will have an negative impact on at least one of the project objectives. It may lead to the project delay, the budget overrun, and even the failure of the project. Thus, to ensure the completion of the project, the risk response strategies should be taken to cope with these project risks. Generally, the project risk is measured based on its expected loss, which is the product of risk probability and risk loss. Based on these two risk characters, the risk response strategies can be classified into 2 types. The first type is risk prevention, which aims at reducing the risk probability and is applied before the risk occurs. And the second part is risk protection, which are applied to reduce the risk loss. While both risk prevention and risk protection can reduce the project risk, its resulting risk reduction degree and their implementation costs are different. Thus, to achieve an effective risk response, the balance between risk prevention and risk protection should be made. This leads to our research question: how to allocate budget among risk prevention and risk protection. In my research, this research problem is formulated on this figure. As you can see in this figure, the x and the y-axis represent the risk probability and risk loss respectively, and the point O represents the initial project risk. The curve AB represents a certain level of risk that can be accepted by the project managers. It captures the risk response requirement that predefined by the project manager. Thus, the goal of risk response is to reduce the risk from point O to the curve AB. As you can see in this figure, the paths OA, OB, OC, OD, OE, and are all feasible paths that can satisfy the risk response requirement. And the path OA corresponds to risk prevention, since it reduces the risk probability. And the path OB corresponds to risk protection, as it reduces the risk loss. The paths OC, OD, OE are all combinations of risk prevention and risk protection. However, in most projects, the risks can't be removed completely. Thus, to capture this risk controllability, we set a minimal value for both risk probability and risk loss. After setting this minimal value, we can see that the path OA and the path OB are no longer feasible. And thus, the goal of the risk response is to reduce the risk from point O to C to the curve CE, and our aim becomes to find the cheapest path from point O to the curve CE. While considering that the risk probability ranges from 0 to 1 and the risk loss always takes a large positive value, which makes it difficult to compare the risk probability and the risk loss, and it's also difficult to compare the risk prevention and risk protection on the same scale. Thus, we use the ratios mu x and y to capture the risk response requirement and the risk controllability, and simplify this problem on this figure. To find the cheapest path from point O to the curve CE, we will develop two risk profiles, two cost profiles to describe the relations between the cost and effect of each risk response strategy. These two types of functions are a linear function and a nonlinear function. The linear function is based on a common sense that if we want to achieve a higher risk reduction, we need to invest more budget. And for the nonlinear function, we develop it based on a basic idea that after the risk is reduced to a certain level, further risk reduction will require a large investment. Thus, based on these two risk cost function, we formulate two mathematical models. By deriving these two models, we can draw a three-step decision procedure with which the project managers are able to determine the budget allocated to each risk response strategy. This three-step decision procedure consists of the scenario selection, the strategy selection, and the budget allocation. In the first step, the scenarios and the restricted strategies are determined based on the comparison between risk response requirement and the risk controllability. In this step, we will determine the scenarios. As you can see in this figure, for the scenario 1, the MIL means risk response requirement. If the risk response requirement is higher than the minimal risk probability and also higher than the minimal risk loss, we can see that only risk prevention or only risk protection can satisfy the risk response requirement. Thus, in this case, no strategy is restricted. But in scenario 2, the risk response requirement is higher than the minimal risk probability, but is smaller than the minimal risk loss. Thus, in this case, only risk protection cannot satisfy the risk response requirement, and thus we regard the risk protection as a restricted strategy. After determining the scenarios and the restricted strategy, we will go to the second step to determine the best strategy based on the restrictiveness of the restricted strategy. Here, the restrictiveness captures the gap between the risk response requirement and the risk controllability, and a strong restrictiveness means a higher gap between the risk response requirement and the risk controllability, which implies that the restricted strategy can only lead to a small risk reduction, and thus, in this case, we will prefer to select the other strategy. As you can see here, we give an example. If in scenario 2, the risk protection is required, then we go to the second step, which determines the restrictiveness of the risk protection. If the restrictiveness of risk protection is high, we will prefer to select the risk prevention, which is the unrestricted strategy. And in this step, then this leads to the selection of the risk prevention. And if the restrictiveness of risk protection is low, we will go to the right direction, which is select both risk prevention and risk protection. And then we go to the second step. We go to the third step. Similar to the second step, the third step determines the budget allocated to each risk response strategy based on the adapted restrictiveness. Similar to the restrictiveness, the adapted restrictiveness is also a metric that captures the gap between the risk response requirement and the risk controllability. And a lower adapted restrictiveness means a large advantage of the restricted strategy. Here we also give an example. We also take the scenario 2 as an example. If the restrictiveness of risk protection is low, we go to the both strategy, which is in the right direction. And then for this step, we'll determine the adapted restrictiveness. If the adapted restrictiveness of the risk protection is low, we prefer to allocate more budget to the restricted strategy, which is risk protection. Thus, we go to the left direction, which is allocating a higher portion of budget to risk protection and allocate a lower portion of budget to the risk prevention. And for the other scenarios and for the other restricted strategy, we can also determine the budget by following this project decision procedure. Then to validate whether the procedure can be applied in practice, we selected 4 risk examples from the literature and also gather the strategies that suggested from literature and that used in practice. For these 4 risk examples, we also applied our 3-step decision procedure and gives our suggestions based on our model. By comparing the strategies from literature and budget allocation decisions from our model, we found that our model results are consistent with the strategy from literature and the practice, which indicates that the 3-step decision procedure can be applied in real-life projects. Then we also conduct some experiments to investigate the impact of the model parameters. To investigate the impact of the risk controllability, we depict the optimal budget allocation decisions in this figure, where the x-axis means the different values of the risk controllability in risk probability, and the y-axis represents the risk response cost. The line curve depicts the optimal risk response cost, and the bar chart means the optimal budget amount allocated to each risk response strategy. The left part of this figure shows the optimal budget allocation decisions in the linear setting, and the right part shows the budget allocation decisions in the nonlinear part. For the linear part, we can see that the controllability of risk probability has no significant effort on the optimal risk cost. But for the nonlinear part, we found that the impact of the risk controllability in risk probability differs in different scenarios. In scenario 1 and scenario 2, the impact of the risk controllability is reflected on the restrictiveness and the adapted restrictiveness. But in scenario 3, the controllability in risk probability has no effect on the optimal risk cost, since the complete budget is allocated to risk protection. In scenario 2 and scenario 4, we found that a lower controllability in risk probability will lead to a greater investment in risk prevention. Well, with respect to the risk controllability in risk loss, we have observed similar results with the impact of risk controllability in risk probability. And also for the impact for risk response requirement, we have observed that when the risk response requirement is strict, a higher risk response cost is required. To conclude, in this research, we draw a 3-step decision-making process that can be followed by project managers. In this process, the risk response requirement, risk controllability, and the restrictiveness and the adapted restrictiveness of strategy should be paid more attention, and a balance between these 3 metrics should be taken care. And then we found that a Lower controllability in risk loss will lead to greater investment in risk prevention, and a lower controllability in risk probability will lead to a greater investment in risk production. In the future research, we will extend our research based on two aspects. The first is that in this research, we formulate two functions, the linear function and the nonlinear function, to describe the relations between the cause and effect of each risk response strategy. In the future research, we will test the results in a more general case by relaxing these relations. And the second point is that in this research, we focus on the balance between risk prevention and risk protection, and thus we focus on only one project risk. While in real-life projects, the projects will be exposed by multiple project risks. Thus, this mathematical model will be extended to multiple project risks, and also by constructing a risk network with which we can investigate the complex relations between the costs and also examine the effect of the complex relations on the budget allocation among different project risks. That's all I can say about my current research. Thank you for your attention, and questions are welcome.